this module we will take a closer look at lift and lift effects, and three distinct things we want to cover here in this little video are the lift equation, as you will need it for your exercise, the lift curves or graphs, and then the foil simulator that is part of the voluntary part of your exercise. Change to black here. First off, the lift equation on page 43 in your book, equation 4.1, lift being equal to the coefficient of lift times dynamic pressure times surface area, and then they figured that even further for you, basically being the coefficient of lift times your density ratio times the square of the velocity. 295, you can already see it's a conversion factor in here, and it tells you that the result will be in pounds, and it also includes that your velocity basically goes into the equation here in knots, as it says on the top of the page there, airstream velocity v in knots. So those are the assumptions that we talked about before and the limitations of that one. So that one is in knots already figured for you, as it says in square feet, as would be to be expected, and the rest is pretty much straightforward. Coefficient of lift dimensionless, and reading the text you should get why it is dimensionless and why it helps us to be dimensionless. Again, the Aerodynamics for Naval Aviators is a really good book in this case, especially for this module, to read up on some of the concepts behind that might be a little bit more shortcut in the flight theory book, especially when we talk about lift, the effects of different airfoil shapes, like increasing camber or putting flaps, slats or other devices on there. Then the Aerodynamics for Naval Aviators book makes or does a really good job in covering those different effects and discussing basically the outcome for our lift. For us here, for the exercise, the most important thing is to properly understand the relationships in that lift equation here, and to point out a couple of things here. First thing is the lift is directly proportionate to the coefficient of lift. So if coefficient of lift goes up, then lift goes up by an equal amount. It is proportionate to the square of the velocity, which basically means if velocity goes up, then lift goes double up. Not double up, but by the square of it up, to be precise. So a small change in velocity results in a big change in lift. That's the big thing to take out of here and keep in mind. And then the third thing that is obviously going in, and or the other two things that are in, is the surface area, which is pretty much a combination of chord length and wingspan in some way or another. If we talk about the wing only and not including other lifting surfaces, like the fuselage or other parts. But for the lift of the wing, the surface area is basically a rectangular function of some form of wingspan times some form of chord length of a rectangular wing, or anything that is similar to a rectangular wing in that case. And then the density ratio, again a dimensionless factor, as we covered in last week's atmospheric conditions. And the density factor, basically, as we know by now from our atmospheric discussion, is a result of three different things. It's non-standard pressure distributions, so basically our altimeter settings, that goes in here, or is part of the density factor that one of the things that can influence our density ratio. The second thing is temperature, that might go in here, and the third thing, as we saw, was humidity. Even though for most of our applications we are not going into the details of humidity, but we've seen last week in our discussion how humidity, or in our exercise, how humidity in the calculator could affect density as well. Again, temperature and pressure being the two big things here, and then the altimeter setting, but also overall what altitude, what density altitude we can correlate our performance to. That's basically the important thing that goes in here. So with the change in altitude, there's obviously a change in lift. As we go up in the atmosphere and the air gets thinner, there's less lift produced, and that's basically what the equation directly tells us. If density goes down, or if the density ratio goes down, then our lift will go down. So as we go up in atmosphere, up in the atmosphere and get to less dense air, then our lift will be correspondingly smaller. And those are the big things, and again the 295 is a constant in here, so we don't have to worry about that one. And that's the big relationships that I want you to take out of the lift equation. So when looking at the equation, you can directly tell speed has a big influence, and the other three things, the coefficient of lift, the density in the atmosphere, and your surface area, have equal and proportionate influence on your lift factor. Once you've found a wing, or once you define the wing, most probably your surface area stays relatively constant. So really the three big things that we're looking for in our exercise, and what the exercise aims to figure out, are those three things here: coefficient of lift, density, and velocity. And those are basically the different parts of your exercise. One last point here: when looking at the equation can help us also in another sense. If we know the lift, then we obviously can work the equation algebraically, like any other math formula that we encounter, and solve, for example, for speed here by dividing by S and dividing by CL. So lift divided by S and CL. That's leaves us this part, and then if we take it times 295 and divide by the sigma, then we solve basically for V square. Don't forget to keep the square there, which is 295 times the lift divided by sigma times surface area times CL here. So basically I just moved, to make it one more time obvious, I moved this to the other side, moved this to the other side, then I moved this to the other side, and the sigma to the other side, and basically that solves algebraically my equation for the square of velocity. So in order to come up then with the velocity, I can build the square root of the whole thing, and that's pretty much what you find when looking at the next page in your book, page 44, where you have the equation solved for the stall speed, with the only difference that we are not looking at any CL, but basically at the CL max at which the stall happens. And that's how you basically get from the lift equation to the stall equation, and both of them are equally important and equally important to know how they apply to us. Again, I just wanted to show real quick how you get from one to the other, and both of them, I would keep a sticky note in your book for follow-on examples, as well as midterms and finals, because both of those equations are important. How do we know now the lift? That's the more important question here, which is which is well discussed in your aerodynamics for naval aviators, but not so much in the flight theory. By our definition, or by our initial considerations, we said if we want to fly an aircraft anywhere, then we need an equilibrium of lift to weight and of thrust to drag. We're not that concerned right now about thrust and drag, because right now we are just looking at the lift weight kind of thing. We will talk about thrust and drag in the next two modules when we start talking about the drag and then also about the performance. But for right now, we want to offset basically the weight, and that's basically what tells us how much lift we will need. We need as much lift as is necessary to offset the weight. So lift in this case in our equation, when we use it for practical purposes, for an aircraft in flight or an aircraft that is in equilibrium of forced flight, then lift equals weight. So the weight of our aircraft directly tells us what the required lift is, and that can be used to, for example, calculate the stall speed in this case. So that's the big thing to keep in mind. Anytime you are asked for something else than calculating the lift under given conditions, and you need the lift somewhere in there, then take a closer look. Are you in equilibrium flight, or are you trying to get to equilibrium flight? If that's the case, then your lift should be the same as your weight, so that answers the question where that variable comes from. And it's not a variable anymore, but you can use basically the constant weight of the aircraft in there instead of the lift. Good. That's for the equation and how to use it and how to get from one state of the equation to another state. And you will need that during your exercise and during your assignment. So again, the assignment this week is aiming to assess your understanding of, as one of the three parts it's aiming to assess. The first part it aims to assess is your understanding of the lift equation and how those different variables relate to each other within the lift equation. The second part it's aiming at is an understanding of the lift curves and the diagrams involved with those. And in general, you find your lift diagrams in the form that you have your alphas, your AOAs, in relation to your coefficient of lift, or your coefficient of lift as a result of changing AOAs in your diagrams. First thing to figure is where's your 0 point, your origin for your diagram. Different depictions might put it at different places. For example, just a hand drawing here real quick. There's, for example, one depiction which has all the scaling on the outside, and then it tells you down here is 0 and down here is 0, so your origin for that diagram would be here. So don't be thrown off by different depictions of the same thing. This right diagram is basically the same way, or a different way of depicting the same information as the left diagram, just that your axes are not going through the origin. But that shouldn't hold you back. If you want, you can pencil yourself in your other line here and make it look like the original. So that's just as a side note. And then you've got your lift curves going in there in different ways, and all the lift curves have a couple of similarities. The first similarity is straight or linear portion in the beginning, then a curved portion on top, and then a fall off towards the right side. So what does that tell us? We have a portion on our lift curve, a linear portion on the lift curve, in which the coefficient of lift is directly proportionate. As we said before, linear relationships basically mean direct proportionate to a change in angle of attack. So an increase in angle of attack will lead to a similar increase in coefficient of lift. and a decrease in angle of attack obviously to a decrease in coefficient of lift. And that actually extends also somewhat into the negative side here. So at negative AOAs, there's some negative coefficient of lift development. Then the second thing is there is somewhere here a maximum, and from differential we can we know what the maximum, or from analytical geometry we know what the maximum of a curve looks like, but we're not really interested in doing any fancy math here. The big thing is to notice that there is a maximum in the curve, and that maximum is has two things, or has one effect. It has the maximum coefficient of lift that we can reach with that airfoil. There is no points on top here, so you can't get more coefficient of lift than that one. That's why we call this thing also CL max, for maximum coefficient, and it happens at one designated angle of attack, which is our stall angle of attack. So your maximum point basically tells you where the stall is happening and what the maximum coefficient at that stall angle of attack is that you can reach with airfoil, which is again important to know, especially when you go into the stall speed, which is basically the lowest speed at which we can fly. To explain that real quick, as a side note here, so when we talk about stall and stall speed, we want to fly the aircraft as slow as possible. So we set in equilibrium flight, our lift has to be, or our weight has to be offset by the lift. So all of our weight has to be basically offset by the same lift. We didn't change, since we didn't change the surface area of the wings. We have basically, and we didn't change the altitude because it's basically happening at one altitude. We have basically a relationship that depends on two things in here. That's the speed, and that's the CL, and the speed goes in as a square and the CL goes in linearly in direct proportion, and then there's some constant which we said we don't really have to worry about right now. So the idea is, again, when we go into the stall speed calculations, that the lift is basically given by the weight, and as we start decreasing the speed here, the lift has to stay the same to still offset the weight. So the lift stays constant at the same thing. So the only way to, since this is a constant and this is a constant, the only way, if this one goes down, then this one has to go up, and it not just has to go up, it has to go up in a bigger amount, since the velocity goes in as a square. So a small change in velocity would make a big change in lift. So to offset that big change in lift that would happen, we have to change the coefficient of lift quite dramatically at that point. And that's the whole relationship that we're looking at, that indirect proportionate relationship to between the velocity square and the CL, the coefficient of lift here. Which also means there is a certain, or as we decrease the speed, the coefficient of lift has to go further and further up. However, we said that there is a limit to how far we can push that coefficient of lift. That's obviously the coefficient of lift max point here in the curve. So once we reach the coefficient of lift max, we can't decrease the speed any further, because we do not have more coefficient of lift available to offset for the further decrease. And that's why that coefficient of lift maximum point becomes also the point where we can reach the minimum speed, or the stall speed. And that relationship is important to recognize. So as we start decreasing the speed, we have to increase the coefficient of lift to still be able to offset our weight. That's what we basically said. So our lift stays constant, the same as the weight, so that we can be airborne and keep flying basically. As we go down in speed, we have to go up in coefficient of lift.